Okay, so in a Unix system, each process has a parent. So when the system starts, it's going to start a root process that is called init, the initial process, that's going to be the parent of all processes. So the system will first create that root process that is the parent of all processes, and then all other processes are going to be children or grandchildren of this. So if you log in, then the login is a process that is a child of the init process, and if you start a command line or a shell, then that shell is a child of the login process, because the login creates the shell, the command line interface. And if you start an application at the command line, if you start an application like Emacs, then that application is a child of the shell process. So very much, each process is a child of another process, and the concept of creating a process is important. Now let's look at how processes are created in a Unix system. So we have the fork system call that creates a new process. So we have a parent process, a process at some point that executes fork. So when it executes fork, or when it makes the fork system call, when it makes the fork system call, it will start a child process. And then both the child and the parent are running concurrently. And we need to understand what it means for these two processes to be running concurrently. Now the point is, running concurrently means that they are both active and they are competing for the CPU. So if the system has a single CPU, then it will be impossible for the parent and the child to be running at the same time. So at any point in time, there is only one process on the CPU. But the system may be doing some switching. If it's a time-sharing system, so the system may be doing something like this. So this is the parent, then kernel, then child, then kernel, then maybe some other process, like process X, then kernel, then child, then kernel, parent. So if you have a single CPU, and how long is this time quantum, by the way? As we will see, this time quantum that each process gets on the CPU is going to be in the 10 millisecond to 100 millisecond range, which means that it's going to be a small fraction of a second, or multiple context switchings are going to happen in 1 second, which means that it's something that you will not feel. So in assignment number 1, in the first assignment that I will be posting over the weekend, we will have a parent and a child. And the parent will be creating a child using the fork exec pair of system calls like this. So in our assignment, so this is the parent that is doing the fork. In our assignment, the parent is going to be a producer and the child is going to be a consumer. And what will the producer do? It will just produce some random numbers. And it will write these random numbers in a shared memory block. And the consumer will be reading these random numbers from that shared memory block. So we will have a producer and a consumer communicating through a shared memory block. That's what we will be doing in assignment number 1. Now we need to understand this fork, this method of creating a child. Now the point is, once the parent makes the fork system call, when the fork system call returns, now we will have two processes that are running concurrently. So running concurrently doesn't mean that they are physically running at the same time. It could mean this, that the system is switching between them, and they are competing for the CPU, and which process gets the CPU, that's up to the scheduler. But they will be both active at the same time. And the return value of the fork, this fork will magically return 0 to the child, and it will return a number greater than 0 to the parent. So one way of illustrating this is you have your parent in memory. This is memory. This is memory, this is CPU. You have your parent. So suppose that this is the address space of the parent, and to simplify things, let's assume that the address space of the parent is just this, A, B, C, D. Once you fork, the system is going to create a totally new address space for the child. And what will it put in that? It will put a copy of the parent's code. So it will put A, B, C, D. So it's basically cloning. Fork does cloning. So it clones the parent. Now there is a child that is a clone of the parent. It's executing the same code. Now, what if you want the child to run a different program, which is what we do most of the time? Most of the time, we don't want the parent to just run the same code we don't want the child to be running the same code that the parent is running. We want it to just run a different program. So that's where we use the exec system call. The exec system call is going to load any program that you want into the child's address space. So you just specify the path to that executable. And then the system is going to replace this with the code for the program that you will be loading, and that's going to be something different. So it could be, F, G, H, I, maybe. Something different than the code of the parent. And this is what we will be doing in assignment number 1. So in assignment number 1, this is the producer code. Producer. And then we will use the exec to load the code of the consumer. So we will have a producer and a consumer. I will talk about the assignment in greater detail in next week, but now I'm just trying to present the main idea. There will be a producer and a consumer running concurrently. So we will be using the fork and exec to load the consumer code. So each one of these is going to be a separate executable. So we will have a producer.exe and a consumer.exe. Two different executables. Okay? Now, what I would like to point out here is that in this case, the parent is launching a child. Then the parent is not doing anything. It will just wait for the child. So this example just is useful for showing us, how the fork exec pair of system calls can be used, but it's not doing anything useful. Because think about it. When there is a parent that launches a single child, and then the single child is doing the work and the parent is not doing anything, what's the point? We only have one process running. Normally, we use forking and multiprocessing in order to run things in parallel or concurrently. You will later understand the difference between parallelism and concurrency. But normally, like we will do in the assignment we will be doing something useful. Like the parent is a producer. Our producer is going to launch the consumer. So here it's going to launch a consumer. Then the parent, the producer, will not be just waiting. It will produce. So here, before it goes to waiting, it's going to produce some numbers. And then, as it's producing, it expects the consumer that is running concurrently, because the system is probably switching between them. Or in fact, if you have a multi-core processor, the system will not be switching like this. It will most of the time, each one of them will be running on a separate core, on a different core. You have and I think all of you will have a multi-core processors. If you have a multi-core processor, then each one of them will be CPU 0, CPU 1. So if the system is doing the scheduling right, then the parent will be spending most of its time on CPU 0, and the child will be spending most of its time on another CPU, and then there will be true parallelism. And this will be producing and this will be consuming. So it's like if there is 1,000 numbers, the producer will produce maybe 10 numbers, and the consumer will consume the first 10 numbers, then the producer will produce more numbers, and so forth. Okay, so now we will look into process creation on Windows, which I find more intuitive. By the way, the fork style wasn't intuitive for me when I first saw it in my OS class more than 20 years ago. I didn't think it's intuitive. I found it odd because it's you are forking and you are creating a different process, and it was hard for me to digest how below this point there are two different programs that are running, but they are executing the same code. So it's not very intuitive. While the Windows, at least it wasn't intuitive for me, but the Windows style of creating processes is more intuitive. So it's just the parent will create a process, and among the parameters that it passes is a complete path to that process, to that executable, and that's it. So it just starts a new process, and that's the executable, and then this is still the parent code. So on Windows, they are not assuming that when you create another child, the child will be a clone of the parent. On Windows, they're assuming that whenever you create a child, the child is going to be a different process running a different program, which could be. There is nothing that prevents it from loading the same program. So you can still, loading the same program is still an option. You can load the same program if you want, but 99.9% of the time, you will be loading a different program.
So is that kind of wasteful? It seems like with the way that C does it, you fork, you create a clone of the same program, then you have to override that with the XClip. Mm-hmm. Isn't that kind of a waste because you're doing all the you're loading this program as a clone and then you're overriding it again? Is that?
Yeah, well, but it's minimal. So this happens only once. Anything that happens once, it's not gonna affect performance because it's like it happens when you first launch the new program and then both programs are running. But I don't know exactly why it was designed this way. I don't know why they were assuming that most of the time the child will be running the same code. I don't know. I don't know. I don't understand the philosophy. I can use it, but I don't understand the philosophy behind this. But just it's interesting to see to be aware of the difference between the way Unix creates processes and the way Windows does. And same thing here, it's going to wait for a single object. Of course, it's a different system call, the name is different, but the parent again is waiting for the child. So again, this is not a useful program because the parent is not doing anything useful before waiting for the child. So, by the way, so when the parent waits for the child here, maybe this is obvious, but when it waits for the child, the state of the parent will be waiting. So the parent, so it's like, wait is telling the system to take the parent off the ready queue. So wait means take me off the ready queue, put me in the waiting state, it should be obvious because the system call is called wait. Okay, so we'll talk now about process termination. When a process terminates, it makes a system call to tell the system that it's terminating, like the exit system call, and the exit can return a code that indicates the status, whether it's normal termination or abnormal termination. When a process terminates, the system is going to deallocate all the resources that are that it has allocated to the process, but it will still keep the process in the process table. So there is a process table that has an entry for each process in the system. It will keep it because the parent may need it. So basically, because usually the parent waits for the child, so the system will keep the entry in the process table, so that when the parent calls wait, the parent will have access to the exit status of the child, whether the child exited normally or abnormally. In some cases, the parent may terminate the child. A parent process may terminate a child process, and why would the parent do that? One of the reasons is that the task that the child is doing is no longer needed. In fact, we will be doing this in assignment 2, not in assignment 1. But in assignment 2, we will be doing this at the thread level. So it will not be a parent process terminating a child process. It will be a parent thread terminating a child thread when that child is no longer needed. Because in that assignment, we will create multiple threads that will search for something. And if one thread finds that key that we are searching for, other threads are no longer needed. So the parent thread in that case will terminate the child threads because they are no longer needed. So some systems do not allow the children to exist if the parent terminates. So some system would terminate the children and the grandchildren when a parent terminates. And luckily this doesn't happen in real life. Otherwise, if someone dies, then nobody's going to kill all the children and grandchildren. But this is something that some operating systems do. Because here this points out that the parent-child relation in operating systems is not exactly the same as the parent-child relation in real life, which means that probably the choice of the words parent and child here wasn't a big choice, because the relation is just not the same as the relation. It's probably similar in when you look at this tree. Well, in real life there is a family tree, but even here, in real life you have two parents. In here there is only one parent. So even this, there is a difference. Anyway, so maybe the choice of the words parent and child was not fortunate. Okay, but people have been using this term for decades in the context of operating systems, and in the also in trees, in binary search trees, and we use parent and child. By the way, when we draw trees in the computer science, we draw them backwards or upside down, right? Because a natural tree doesn't have a root at the top. Have you thought about this? In your data structures class, right? The tree has the root at the top, but in nature, it's the other way around. Yeah. Now the notion of a zombie and an orphan. So if a child terminates before the parent calls wait, then it's a zombie. So this is a parent. This is a parent, and let's do this. Parent and creates a child. Now this is the child and the parent. They're running concurrently, but say the parent calls wait at this point because the parent does other stuff while the child is doing its work, which is what we will be doing in the assignment. Parent will be producing, child will be consuming. But then if the child terminates before, so in our assignment it will not be possible because the consumer is dependent on the producer, so the consumer cannot consume something before it's produced. Right? So in our assignment, the child cannot go ahead of the producer. The consumer cannot go ahead of the producer because it's dependent on it and it cannot consume something that it hasn't been produced. But in general, the child may terminate before the parent calls wait, and in this case, if it does exit and terminates, during this time period between the exit and the wait, so this time period, so during this time the child is a zombie. It has terminated, but its parent has not yet called wait. Okay. Now, if a child terminates and the parent has terminated without calling wait, then in that case, it's an orphan. Like in real life, a child without a parent is an orphan, because in this case, that child will have no parent. And in some systems, for example, in some Unix systems, if there is a child without a parent, then the system will assign the init process, which is the grandparent of all processes in the system. It will be the new parent. Okay, so it's like the government taking care of an orphan who has no parent. And in this case, the system is like the government. So this is an example that shows us the power of multiprocessing, why we want to create multiple processes. And the example here is the Chrome browser, which takes advantage of multiprocessing to have, so it has a main process, a main browser process that manages the user interface and the networking, but it has a renderer process, a separate renderer process for each page. So each of these pages has a separate renderer process, which means that if there is a problem with one of the websites, or the server for that website is slow or down or whatever, that's not going to affect the rest of the pages. So this is where we want to have, where multiprocessing is very useful. Now we talk about inter-process communication. So there are two methods of inter-process communication: shared memory and message passing.
So by definition, fork creates only one child?
Yes, only one child. And if you want to create multiple children, you have to call it multiple times, but you have to be careful because once it forks, it creates two different processes. And if you fork after that, then each one of the two will fork. So you'll end up with four. So it's like a fork, then each one will. So fork does this, then when you fork again, each one of them is going to fork too. So you have to be careful about multiple forks.